All right. Good morning, everybody. So, how is your day so far? I hope it's going well. But I heard that you finished section 8.2 today in the lecture, which might be quite a lot to digest at this point. And then you also started section 8.3, which is about trigonometric substitution. So what I plan today is to wrap up our discussion of integration by parts and then proceed to some examples of integration of some powers of trigonometric functions. And for that purpose, I have uploaded the blank worksheets 9 and 10 in my website. These blank worksheets correspond to the exercises from the textbook covering trigonometric powers and trigonometric substitution. So you can check them out there. And yeah, and actually we finished grading the free response part of your test. So our lead TA will start uploading them back to CASA so that you can see them. I don't know if it's already available, but it should be in a couple of days, so you can see it there. So now back to business. So we'll wrap up our discussion of integration by parts last time. Um, but I hope as we go along section or chapter 8, you should be able to at least have an idea of for which integrals will this method be more applicable to, because in the exam there's a big chance that you will just be given the integrals and will not be told what method to use, and we will be dealing with 3 or 4 methods in this chapter. So if you mix them up, it's easy to get lost and waste some time on thinking about what is the proper integration technique to use for a particular problem, right? So if you go back to integration by parts, it is commonly used when you're integrating a product, right? You will imagine the original integral as the integral of u times dv, right? And integration by parts formula 1 on the screen tells us that that integral can be evaluated as uv minus the integral of v du. And we are hoping that with the proper choice of u and dv, the integral on the right-hand side of equation 1 is much easier to evaluate, right? So that means your integral of v du should be elementary, or it should be easy to integrate. So this method actually boils down to choosing the u and the dv properly. As a general rule, you choose u to be the function that can easily be differentiated, and dv is the function that can easily be integrated. Because remember, we will need we will need we will need du and v for formula number 1. So you should be able to compute those things easily, right? Another guiding principle in choosing the u function is the acronym ILATE. So this tells us the precedence for choosing the u. So you start with inverse trig functions, followed by logarithms, then algebraic functions, trig functions, and lastly, the exponential functions, right? And I guess last time we have seen some examples, and I included in this worksheet the 32 problems you will see in the textbook. I guess this is more than sufficient practice. So try to see if you can answer these in preparation for the next test. Then we look at some examples. Probably I'll close the discussion with IBP, with some of the commonly asked questions that the students sent me, either from this lab or my other lab or from the CASA Tutoring Center that I man every Tuesday and Thursday from 6 to 7 p.m. So, but if you have specific questions about IBP, let me know. We can probably devote half an hour today answering these final problems about IBP. But while waiting for those or for your questions, let me answer these additional problems. So I'll call it additional problems so that the numbering will not be consistent with the worksheet. So the first problem is the integral from 0 to 1 of x ln of x plus 1 dx, right? I don't remember if we did the definite integrals last time, but this is one example wherein my personal preference is to forget about the bounds for now, compute the antiderivative, then apply the fundamental theorem of calculus later in the game. So what I'm trying to say is here I will consider the integral of x ln of x plus 1 dx first, forgetting about the bounds for a moment, so that I don't need to keep track of them every step of the way when I'm doing the IBP, right? And then in this integral, we will use integration by parts. Remember, we have the acronym ILATE here. And let's see what we have here. The first function is x, which is algebraic, so that's the letter A. The second is ln of x plus 1, that's a logarithm. And L precedes A. So here I will take u to be equal to ln of x plus 1, right? And dv to be just x dx, whatever remains, right? And then I'll compute du. Du will just be 1 over x plus 1 dx. And then v will be x squared over 2. All right. Now, if we apply formula number 1 for IBP, the original problem, or the original integral, is equal to uv, that's x squared over 2 ln of x plus 1, minus the integral of v du, so that's x squared over 2 times 1 over x plus 1 dx. All right, and then, yeah, Kevin, I'll go back to problem 21. Thank you for the suggestion. So here I'll have x squared over 2 ln of x plus 1 minus 1/2 integral of x squared over x plus 1 dx. Right? And we're hoping that this integral here is much easier to evaluate. Right? A common mistake students do whenever dealing with integrals like the highlighted one is that they write it as x squared over x plus x squared over 1. You cannot split a quotient like that. You can only do that if the denominator is a monomial. But clearly here, the denominator contains 2 terms, so you cannot simply split it up into 2 pieces at this particular point, right? So what they'll do here is in the highlighted integral, I will let u to be equal to the denominator, giving us du equals dx. So the integral of x squared over x plus 1 dx is equal to, I'll do the u substitution, so dx will be replaced by du, and then I'll have u in the denominator over there, right? But we need an expansion for x squared in terms of the variable u. If you go back to the substitution statement here, you can solve for x, so we see that x is equal to u minus 1. So x squared can be replaced by u minus 1 quantity squared. That's what I'm going to do here. The x squared in the numerator can be written as u minus 1 quantity squared. And then I'll expand the numerator, so I'll have u squared minus 2u plus 1 all over u du. And this is what I'm referring to earlier. When the denominator is a monomial, you can divide all terms in the numerator by that monomial factor, or that monomial denominator, right? So what happens here is that we will simply be integrating u squared divided by u, so that's going to be u, minus 2u divided by u, that's 2, plus 1 over u du. Good? And now we can easily integrate this. This is u squared over 2 minus 2u plus ln of absolute value of u plus c. And this is what the integral of x squared over x plus 1 dx is, right? And of course, we need to go back to the original variable. Remember, we let u to be equal to x plus 1. So this is x plus 1 squared over 2 minus 2 times x plus 1 plus ln of absolute value of x plus 1 plus the arbitrary constant c. But this is just one piece of the integration by parts that we are trying to do. So let me just go back there. Remember, this is what we are evaluating. Right? And we said using by integration by parts, that thing is just equal to this. And I love that copy pasting is possible here. But remember that the highlighted integral was evaluated before, right? That thing is this guy. Then we can just write the plus c over there, right? Because c is just a random constant. So if you multiply it by negative 1/2, it's still a random constant, right? So I can write it in this form. Then I can simplify a bit. So this is x squared over 2 ln of x plus 1 minus x plus 1 squared over 4 plus x plus 1 minus 1/2 ln of absolute value of x plus 1 plus the arbitrary constant c. Okay, so just make sure that I did the arithmetic right. I think you know by now that my arithmetic is a little bit sus, so kindly check that. But again, remember we are after the definite integral. Right, so we began with evaluating the integral from 0 to 1 of x ln of x plus 1 dx. But we know an antiderivative, so this entire thing here is the antiderivative. I'll just apply the fundamental theorem of calculus for this. So remember, all I need to do, find an antiderivative, and that's what we did in the previous step. Evaluate it from 0 to 1. So I plug in 1 first, so we'll get what? We'll have 1/2 ln of 2 minus 2 squared over 4, so that's going to be 1, plus 2 minus 1/2 ln of 2. And then minus, I'll plug in 0, so I'll get 0 there. I get minus 1/4, then I'll get the plus 1, and then I'll have a minus 1/2 ln of 1. Okay, and let's carry out the simple arithmetic here. 1/2 ln 2 minus 1/2 ln 2, they will cancel each other. And then so this would be just minus 1 plus 2, so this would be positive 1. Minus what happens on the second group. Ln of 1 is 0, so this thing goes to 0. And then this is 0, so we'll just have minus 1/4 plus 1. That's positive 3/4. So we have 1 minus 3/4, so this would be 1/4. So that's going to be the final answer. Okay, is that clear? Okay, so I guess here Kevin suggested we go over problem 21. Let me just browse back to the problems. I haven't done problem 21 in the lecture yet because this is one of the problems that is usually discussed in the lecture. But yeah, if you haven't done this in the lecture, then let's do it here. We want to integrate arcsine of x dx. Here we don't have any choice but to use IBP by taking u to be equal to arcsine x, and then dv will just be dx, right? Because you cannot let u to be equal to dv. You cannot let dv be equal to arcsine x dx, because remember, dv should be easily integrable. And you cannot put dv equals arcsine, because to find v, you will end up evaluating the integral of arcsine x dx, which is what we started with, right? So here you don't have any option but to let u to be equal to arcsine of x. So the next step is to compute du. Du would be the derivative of arcsine x, which is 1 over square root of 1 minus x squared dx. And then v is equal to x. Okay, so you want to be an x in front of the arctan. Okay, that's fine. Delete. So I'll call it problem 2. But hopefully this is integrable, because not all problems can be solved by IBP. So let's see if we don't get stuck anywhere here. So, okay, so if that's the case, then I still will choose u to be equal to arcsine, because remember, ILATE tells us that inverse trig functions are the prime candidates for the u, okay? So the only change here would be dv will be x dx instead, right? So v is x squared over 2. All right, all good. Did you encounter this problem somewhere, Kevin? Because I am hoping that this is easily integrable. So let's see. Now, using IBP, so the integral of x arcsine x dx will be uv, so that's x squared over 2 arcsine of x minus integral of v du. So x squared over 2 times 1 over root of 1 minus x squared dx. Okay, so we'll have x squared over 2 arcsine x minus 1/2 integral of x squared over root of 1 minus x squared dx. And here is where I am a bit worried about. Can we evaluate the integral of x squared over root of 1 minus x squared easily? So for this problem, one choice is to let u to be equal to 1 minus x squared, but that will only require a 2x dx in the numerator, which we don't have at this particular point. So what would be the other choice for substitutions? Because I'm thinking that this might require trigonometric sub, which is section 8.3. So let me do a calculation quickly. I want to start the long solution without knowing if what I'll try to do will work. Yeah, I guess this is fine. I'm thinking here another IBP application will be required. Yeah, but yeah, no trigonometric substitution will be required here, because we can apply another round of integration by parts here. So no worries, Kevin. I can still continue this because this is a good practice problem, I guess. So here we have this to worry about right now. So let's do that. I'll use IBP once more on that integral, on the, let's call it the yellow integral, so that I don't have to write the highlighted integral that's quite longer. Right, so but here I will take u and dv. I don't think ILATE will work here because both of them are algebraic. But the main guiding principle in choosing the u and the dv is that u should be easily integrable, and dv, u is easily differentiable, and dv is easily integrable, right? So I guess here I can let u to be equal to x squared, and then dv is 1 over square root of 1 minus x squared dx. All right. Now, du is equal to 2x dx, and then dv And then v will be the integral of dv, but this integral is just arcsine of x. All right. And that's why I chose dv to be equal to 1 over root of 1 minus x squared, because we know that that integral, or the integral of that that square root function, is just arcsine of x. Okay. So the yellow integral, x squared over root of 1 minus x squared dx, can be written as x squared arcsine of x minus integral of v du. That's going to be 2x arcsine of x dx. v du. All right. Or you can rewrite it as x squared arcsine of x minus 2 integral of x arcsine x dx. But hold on, do you remember this integral? This integral happens to be exactly the original integral that we're trying to compute, right? So this is a usual variation of the IBP, wherein in one of the iterations of the integration by parts, you come across again with the original integral, right? So, and this is what we can do. So remember, let's retrace our steps now. We're calculating the integral of x arcsine of x dx. And so far, we learned from before that that is equal to this guy. Okay. And what we did in our previous calculation is to calculate the yellow integral, right? But now we know that the yellow integral, I should have deleted, is equal to this. Oops, sorry. Oh, but there would be a problem here. And I'll show you why. So this is x squared over 2 arcsine of x minus 1/2 x squared arcsine of x plus integral of x sine of x dx. I was hoping that what we can do here is to try to put this to the left-hand side. But you see, what would be the problem if I do that? If I transfer that to the left-hand side, I will have a 0 on the left. And what do we get on the right? We get 0 on the right. So we come up with a 0 equals 0 equation, which is totally crap, right? Because that won't give us any integral left, and we don't know the expression. If this was a minus, or it comes with any other constant multiplier, I can put it on the left-hand side and just divide everything on the right by whatever that constant on the left, right? To get the integral of x arcsine x dx. And that's what I was hoping to happen here. But it seems that I'll get the identity 0 equals 0 here. So that means even though I did all the steps correctly, I didn't get a good answer. So that means integration by parts simply is not applicable here. Or perhaps a different choice of substitution would be would be better, right? But unfortunately, integration by parts failed here. So you need to look for another method. All right. Yeah, I was hoping that we will not get these results. But anyway, it is what it is. So that's an example wherein you have to look for another method. And the thing is, we have wasted a good 10 minutes trying to do this. Imagine if it was an exam. So yeah, you need to look for another method. But perhaps to evaluate x arcsine of x dx, you need a different method. Right. Let me just see quickly. I'm just curious, what is its integral? X times arcsine x. Yeah, it turns out its integral is 1/4 times x root of 1 minus x squared plus 2x squared minus 1 times arcsine of x, which I don't get nowhere. I don't get there here, so there is another method that should be used. Okay, so let's go back here when we have the proper tools to answer this problem. So, but I hope you learned the process here. So let me see. Have you guys had difficulties with this integral? I'll call this number 2 because I will delete the previous problem from from the worksheet that I will upload later. But have you guys encountered this integral of sine of ln x dx? You had some difficulties with this one? Or you want us to go over this problem? You could have encountered the cosine of ln x dx, but the process is still the same. Hello, guys, are you there? Okay, so do you want to go over this? Probably let's do. Okay. All right, so here this is, we'll use integration by parts here. But again, we don't have any option because we only have one function here, sine of ln x. And I hope by now you are not, you will not be confused and treat this as sine times ln x, right? This is sine of ln x. So the ln x is inside sine. So technically this is a single function, right? It's a sine function with an ln inside of it. So we don't have any choice but to let to take u. I want to use the verb take rather than let for IBP. So here we'll take u to be sine of ln x. And then dv would be just the dx because that's the only thing left. Again, there's no point in letting or in taking dv equals sine of ln x because we need the v. And computing the v will require integrating sine of ln x, which we cannot do in the first place, right? So now we compute for du, and this is fine because we're just differentiating sine of ln x. So this is cosine of ln x all over x dx. Remember, we need to apply the chain rule here. And then v will just be x. So the integral of sine of ln x dx will be uv. So we'll have x sine of ln x minus integral of v du, x times cosine ln x over x dx, right? So I just applied IBP here, formula number 1. And then let's simplify the integral on the right. Oops. So this is x sine of ln x minus integral of cosine ln x dx, because the x's will cancel each other out. And here in this integral, in the yellow integral over here, we need to apply IBP first, right? So in the yellow integral, oops. Perhaps I'll put the quotes here. We use IBP again, right? We take u to be equal to cosine of ln x, and dv is equal to dx. Du then will be equal to negative sine of ln x over x dx. Again, I apply the chain rule there, and v is equal to x. All right, good so far. So again, the integral of cosine of ln x dx is equal to uv. That's x cosine of ln x minus integral of v du minus integral of v du. So that's x times negative sine x over x dx. Sorry, this is okay. Right. And when simplified, this turns out to be this. All right. But do you recognize this guy? Oh, sorry. There's no denominator anymore because the x's cancel each other out. This is essentially what we began with, right? Or what we begin with. You have the integral of sine ln x, which is the original problem. Okay. So if we recall, the integral of sine of ln x dx from the first application of IBP, we got this. Right? But we have evaluated the yellow integral. That yellow integral there is equal to this. All right. Then let's just perform the algebraic manipulations here. So I'll have minus x cosine ln x, and then minus integral of sine of ln x dx. And again, I'm a bit happier at this point compared to the previous problem, because you see, this is exactly the original integral, but it came with a negative sign out of the manipulations. So if I transpose it to the left-hand side, what I'll have is a positive integral of sine ln x dx to be added to the left-hand side. So basically, the left-hand side now becomes 2 integral of sine of ln x dx equals x sine ln x minus x cosine ln x. I'll just put the plus c1 here to account for the arbitrary constant, because there are no integrals left on the right-hand side where I can claim that the arbitrary constant is hiding on. So I'll put a c1 there for a moment. And then now I'll divide both sides by 2 to get the value for sine, or for the integral of sine ln x dx. So this would be x over 2 sine of ln x minus x over 2 cosine of ln x plus the arbitrary constant c, right? Where c can be thought of as c1 over 2, but c1 is a random constant, so c1 over 2 is a random number, and I'll just call it c. All right. Any questions with that, guys? Okay, good. So is it okay if we leave integration by parts for now? But I guess we'll see this method again when we go to powers of trig functions, because there's one particular case there where we need to use IBP. All right. So if that's good, I'll switch to worksheet number 9. Yes, Val, you can leave the integral in that form. You mean, where is that? Yeah, this is the final form for the integral. One particular disadvantage for multiple choice quizzes is, or part of the exam, is that sometimes you need to perform some algebraic manipulation before you get to the form that is given in one of the choices. So that's sometimes a pain. So wherein you need to use some identities in order to get one of the forms in the choices. But if it is a free response question, then you can leave your answer at this particular form. All right. Because when we grade them manually, we take into account all possible representations for the solution, which unfortunately cannot be traced when you're doing multiple choice problems. Okay. So if there are no questions, then let's start looking at examples for integrating some powers of trig functions. So in this we will consider problems wherein we want to integrate the product of powers of sine, like you have sine to the m of x times cosine to the n of x dx. And it depends on the solution will depend on the parity of m and n. When I say parity, it is simply being odd or even. Parity, is it odd? So it means odd or even. That's what we meant by the parity of two numbers. So it depends on whether m and n are even or odd, or what type of combination we have. And then the second part, I think second case that we'll consider would be powers or products of powers of secant and tangents. But the same method also works for cosecant to the mx, cotangent n x dx. So this is the same procedure. Okay, so basically the three pairs of trig functions will be reduced to two types of solutions, right? And let's start with sines and cosine first, and probably we'll do secants and tangents on Friday. Okay. So the solution, let's focus on sines and cosines. The solution will depend on the parity, as I've mentioned, of m and n. If either m or n is odd, meaning if there's at least one of those exponents that is odd, then here's what you can do. So you reserve a factor from the odd power to be the du, right? So say you have sine to the third x, right? So that's odd. So what you need to do is to take one of those signs, and that will be reserved to be our du. So if you're reserving sine to be the du, then you will be letting u to be equal to cosine, right? So that to utilize that isolated factor for the du. Maybe I should not use script here, so I'll use du, right? And then write the remaining factors. Write the remaining even power. Because remember, you started with an odd power. You take one of those factors, so you will be left with an even power. And that's what I meant by the remaining even power. So write the remaining even power in terms of the other trig function, in terms of the other trig function, via the identity sine squared x plus cosine squared x equals 1. So the crucial thing here is whenever you have an odd power, at least one of the powers is odd, then you'll use the Pythagorean identity. Okay. Now, if both of them are even, and that's our other case, both are even, then use the half angle identities. Use the half angle identities. And if you remember from your algebra classes, you'll have sine squared x is equal to 1 minus cosine of 2x all over 2. And cosine squared x is equal to 1 plus cosine of 2x all over 2, right? So you replace all those even powers using these identities so that your power will be reduced by an order. And then you'll try to manipulate the integrand until you get to an elementary form. But mind you, if both are even, it's a lot more complicated, because if both are even, you might need to use integration by parts, or you might still need to use some other techniques in order to evaluate the integral. All right. So it depends on how high the power of sines and cosines are. Okay. Now, I think it is, as always, much easier if I'll show you specific examples. So let's try probably problem 4. Unless you have some suggestions. I just chose problem number 4 because this would be a good introduction to the method. So you see how the process is being applied, right? So here you have powers of sines and cosines. And then you see here that cosine has an odd power, right? So this is case number 1, wherein at least one of the powers is odd. So here, remember what I wrote earlier is that when that happens, oops. Okay, when that happens, what you need to do is to reserve one factor out of the odd power as your du. So I have a cosine cubed. I'll take one of the cosines and reserve it for the du. So what will be left for that odd power is an even power, right? And then I'll just copy the other factor. All right. Just remember, this is being reserved for the du. Okay. And then the remaining the remaining even power, right? Remember, we took one of the cosines, so we'll have a cosine squared left. Remember, I can write this using the Pythagorean identity in terms of the sine function. I can write it as 1 minus sine squared x. And then this guy, I can retain that as sine to the 4th, right? But why did I do that? Because here, I want to let u be equal to the appropriate u. Remember, we reserve a cosine x dx for our du. So expectedly, we will let u to be equal to sine x so that we can use that reserve factor for the du. Right? Okay. So with those in mind, our original integral is equal to, right? So cosine x dx becomes our du. This guy becomes u to the 4th. Okay. And then remember that the first factor, cosine squared x, using the Pythagorean identity is 1 minus sine squared, but we're letting u to be equal to sine x, so this is just 1 minus u squared, right? And that's how this form came about. And the nice thing about this form is that this is just a polynomial in u, right? So you can simplify, so you get u to the 4th minus u to the 6th du, and integrate this is easy, or integrating this is easy. Use the power rule, and then revert to the original variable. Remember, we let u to be equal to sine x, so this would be sine to the 5th x over 5 minus sine to the 7th x over 7 plus the arbitrary constant c. All right. Is that okay? Okay, let's try another one. Let me see. Let me try problem. Let me try problem. Let me try problem 6. So problem 6, integral of cosine squared x times, oops, sorry. Cosine squared x times sine of 2x dx. Here we don't have the right, we don't have the form of a product of two powers, because here we're multiplying a power of a cosine times sine 2x. So before you go any further, you need to try to use identities in order to write it in a form sine to the m times cosine to the n, right? So if you go back to your algebra notes, you can recall that sine of 2x is equal to 2 sine x cosine x, right? That's what I want. I will use here. So I'll have cosine squared x times 2 sine x cosine x dx. Oops. Right? Or that is 2 integral of cosine cube x. What's happening to my iPad? But okay, times sine x dx. All right. And I guess that's the most crucial part that you remember to write the given integral first in terms of a product of powers, and to do that you need the double angle identity. Okay. Now you look at the parity of the exponents. Because Kevin, because I originally have a cosine squared x, right? But sine 2x is 2 sine x cosine x, so I just carried out the multiplication. But actually, I will split it up again after I recognize that, oops, this is odd. Actually, you can do two ways, right? So this is odd, right? Both of them happen to be odd. So case number one still applies because case number one works at least if you have an odd power, right? So here you can, there are two alternative solutions here. First is you reserve this to be your du, that's fine. And then write cosine squared in terms of sine as what we did with problem number 4. But I guess the easier one here is, I guess use this as our du, right? And then a simple u substitution will work here, which is what I did not intend to use here. But anyway, I guess that's the more natural thing to do here, because here you have you have an odd power, sine as exponent 1, which is odd. So you isolate one of them, so that's sine x dx, and unfortunately there's nothing left to be written in terms of cosine using Pythagorean identity, but that is to our advantage. So at this point, I can simply let u to be equal to cosine x, right? Because remember, I am reserving the du to be something that involves sine x, but there's a missing minus sign there, which is not a big issue. So now we'll have negative 2 integral of u cubed du. So this is minus 2 u to the fourth all over 4 plus the constant c. All right. Then we revert to the original expression, to the original variable. So I have a negative sign. 2 and 4 will cancel each other out, leaving a 2 in the bottom. And then u to the fourth, so that's going to be cosine to the fourth of x plus constant c. All right. But again, alternatively, you could have chosen to work with this guy. Okay. Because this is the same as our original problem of integrating, what was the original problem? Cosine squared x, sine of 2x dx, right? So I could have reserved this to be my du, okay? And then the remaining even power will be written as 1 minus sine squared x. I should have used a different color here, hold on, so that you will not be confused which would be part of the solution and which would be just preliminary analysis. So I will reserve the cosine x to be my du, and then I'll write it using Pythagorean identity again as 1 minus sine squared x, okay? And I'll do a u substitution here, a bit differently. I will let u to be equal to sine x, so that I can use as du the reserve factor cosine x, right? So that means this will be, oh, why do we have a 2 there? Do we really have a 2? Yeah, we really have a 2. So this will be u, and then this will be 1 minus u squared. So technically, the original integral becomes the integral of 1 minus u squared times u times du, which is the integral of u minus u cubed du, which is u squared over 2 minus u to the fourth all over 4 plus the arbitrary constant c. Then we revert to the original variables. So this is sine squared x over 2 minus sine to the fourth x over 4 plus the arbitrary constant c, which is also a correct answer. So you can have your answer like this, or you can have this. Both are correct. They are not necessarily equal because remember you have plus c's here. So their difference might be arbitrary constant, but that's fine. Because if you remember, two antiderivatives always differ by a constant. So yeah, these are two perfectly acceptable answers that are not equal to each other. All right. So any quick questions? Unfortunately, it's already time, so I'll just start with an example. We're in both are odd next time. We need to use the half angle identity. Yeah, Bao, you're correct. I guess this is easier than integration by parts. Actually, that happens if for sines and cosines, if one of them is odd, then that's fine. But when both of them are even, and if they are, and the exponents are high, like you have to the fourth and to the sixth, that will entail a lot of calculations. But yeah, that's the only complication I see for powers of sines and cosines. Oh, don't worry, Kevin, about it. Actually, it gave us a nice insight on your x arcsine question, because that tells us that sometimes integration by parts will not work, even if you do the solution correctly, right? But that's perfectly fine. It was a nice review of the process, plus it gave us an insight when it will not work. And if that happens, then you need to look for another technique. And that's the difficulty about integration, because we cannot just invent problems out of the blue, because that might require higher advanced methods, or they are not integrable at all. All right. Okay, so yeah, on Friday, I hope to see some questions from you guys about trigonometric powers, and probably towards the end, we can start trigonometric substitution. Okay. So have a good day, everybody, and let's see each other on Friday. Bye, everyone.
Bye. Thank you.
Thank you.
Right, you're all welcome.